Okay, welcome to Unit 1 of our next unit in physics. It's called Dynamics, where we're going to study forces, pushes and pulls, and of course Newton's laws. So let's look at Newton's first law. An object at rest remains at rest, and an object in motion continues in motion with constant velocity, that is, constant straight speed in a straight line, unless it experiences a net external force. Objects in motion tend to stay in motion. It's also known as the law of inertia. And inertia is defined as the tendency of an object to maintain its current state of motion. Objects resist changes in motion if they have a lot of inertia. It's directly proportional to the mass. Think of me, the couch potato original. So, do these guys have a lot of inertia? Yeah, you betcha. Sumo is all based on inertia. The whole sport is based on it's hard to move one of these big guys. How about a school bus, right? We put you in those big buses for safety because if they get hit in a car accident, they have a lot of inertia. They resist changes in motion. Zzz. How about a mosquito? Now, not a lot of inertia there because it's so tiny. So we can say that more mass, more inertia, lots of inertia. It's hard to get something moving or to stop it from moving or to change its motion. So we need to define force. A force is defined as simply a push or a pull. It changes the state of motion. So there are two main types of forces we're going to study. Contact forces, which are physical interactions between objects. When you push or pull them, there's ones called normal forces and tension forces, and frictional forces. And then there are field forces that we'll study. The one that we've studied so far, an action over a distance, is of course gravity. There are plenty of others, but we'll get into those later in the course. Let's take this example problem. A block of wood is sitting motionless on a table. What forces are acting on it? Well, force is a vector quantity, which means it's represented by an arrow, same way we've represented other vectors. The length of the arrow indicates its magnitude, and the arrowhead indicates its direction. So that force is called a weight, or sometimes called F sub g, the force due to gravity. But there's another force. The weight is gravity pulling towards the center of the earth. The other force acting on it is something we call the normal force. That's the reaction force of the table that exerts on the object when it's pushed upon. So those combinations of forces are balanced if it's motionless. Okay? If there's no net force, if an object is motionless, the forces are balanced. Also, when an object's moving with a constant velocity, we say that that's in equilibrium and there is no net force. When we have an unbalanced force, we get a change in motion. And we call changes in motions accelerations. We've studied acceleration already. It's the rate of change of velocity. So how much acceleration depends upon a couple of factors. The amount of force. You push something harder, you're going to get a greater change of motion. And the amount of mass an object has. Something that's more massive is harder to get moving than something that's less massive. So more mass, you get less acceleration. So Newton's second law can be stated this way. The acceleration of an object is directly proportional to the net external force acting on the object and inversely proportional to the mass of the object. It's stated this way in a physics equation because we have to have an equation for everything in physics. The acceleration is equal to F net over m, or the sum of all the forces acting on an object equals mass times acceleration. Okay, the unit of force is the Newton, named after, of course, Sir Isaac Newton. And 1 Newton is equal to 1 kilogram meter per second squared. So mass 1 kilogram, acceleration 1 meter per second squared. So here's a glass bottle with a mass of 10 kilograms sitting on a counter. What's the weight of the bottle? Fg is equal to mg, g being the acceleration due to gravity. 10 kilograms times negative 9.81 meters per second squared. We get a force of negative 98.1 newtons. What is the reaction force, or the normal force to that? Okay, the countertop is going to push back with a normal force equal to positive 98.1 newtons. And again, the sum of those two forces would be 0, and then we say the object's motionless because it's in equilibrium. Newton's third law, this is the one everybody knows already. For every action, there's an equal and opposite reaction. Here's the forces again acting on the table, and that's the weight of a box that's being suspended on a string. Normal force there, and here's a tension force here holding the box up in the string. Newton's third law examples: if a firefighter is pushing a stream of water to the east, what direction is the force on the hose?